Okay, I guess it's 30. Need these. So my name is Mitchell is my first name. Schoenbrun. I'm not picky. I'm gonna call me. Hey, you is okay. I've been doing math for a long, long time. Been teaching on and off for, I don't know, about, I guess we're going on 7, 8 years. I taught in high schools for a while. Taught a little in San Francisco State. This is my second quarter here, so there's, you know, stuff about school I'm still learning. I have a website, it's my own personal website, which Foothill, this is the part you'll be interested in. You can look at the other stuff, but I don't think you'll be interested in it. Unless you've always wanted to make a telescope, I have a little stuff about making telescopes over there. I kind of came back to teaching math at this level kind of late. I was in my late 40s when I came back and did a master's degree in math. If you're getting your education now, when you're young and good, it gets hard. It's hard to sit in a class when you're, it's fun, but hard. Okay, about this class, everybody here, has anyone here not taken Calc 1A? Everybody, okay, did you place in? The AP, you did place in for the AP.
Yeah.
Okay. All right. You did well on it. Okay. Good. This is the second quarter, mostly integration, which we're going to get into a little today, what that's about. Let's see, a few things about the class. Everybody should know the class is 1:30 to 3:45, Tuesday, Thursday. What I say on the green sheet about office hours, I just discovered it's not going to work because this room isn't open 1 to 1:30. I'll see at 3:45 if it's open, and then if it is, I'll hang around for half an hour each day, you know, or an hour if people need it for office hours. Everybody knows this is the book. You have the book? Not yet. Okay, this is the book. It's a custom version of James Stewart, a very popular book. Unfortunately, you can't get a used one or the standard one. You have to get their book. Everyone should have a graphic calculator. Who brought a graphic calculator today? I have a couple extras, so when we're doing stuff, you'll be able to borrow one. Okay. You should have, it should be a TI, it should be a TI 83 or 84. If it, actually, I guess an 82, which you probably can't buy anymore, would work. And if it has a bigger number, there's a problem. The department doesn't let you use anything beyond an 84 on exams. You can use it for homework and so forth. The reason is it does some things automatically that we want you to learn how to do. And we can't make you learn it if you can just punch it in your calculator. All right. Well, it's a problem for anyone, let me know after class. I think everyone should have a green sheet. Does anyone not get a green sheet? Okay. A copy. think actually what I'm going to try and do very quickly is take attendance. You may have noticed this is a very small class. I like to not think that after the last class I taught word got around. No, actually, it's just the way it was set up. I was the last. All the other classes filled in, and then they created this class. Okay, if I pronounce your name wrong, let me know, and I'll try and fix that. Andrew.
Andrew.
Yeah. I'm just gonna say the part of your name that I think I can get right without embarrassing myself too much. There, Benjamin. Benjamin is here. Arden. Is there an Arden here? Okay, no. Mohammed?
Here.
Okay. Austin? Here. Austin. Matthew?
Here.
Matthew. Daniel?
Here.
You're not Arden, are you? Arden?
No.
No. Okay. Merdad? Merdad? Okay. Brandon? Okay. So I'm going to try my best. Tuan? Okay. It'll take me a couple seconds to get that right. Shabri? Shabri? Okay. Christina? Bruna Caroline? Okay, is that one name or?
Bruna. Bruna is fine.
Bruna, okay. And Israel. Okay. If I didn't say your name, raise your hand. So, okay, your name is?
Catherine.
Catherine?
Yeah, with K.
Mm-hmm. Last name?
Liu, L-I-U.
Say that again?
Liu, L-I-U.
L-I-U. Okay, and
Daniel McGill.
Daniel. Okay. I don't have add codes today. I didn't think I'd need them, but I'll try and bring an add code Thursday. And Arden is not here. No. So 2, 4, 6, 8, 10, 12, 14, 15. Very small class. I think that'll probably be good. All right. What can I say without just repeating this? You'll notice from my grading policy, I do want you to do homework. I do give you some credit for it. But to me, homework isn't a test. Homework is about practice. And you should do it. Unless you're some kind of genius, you're not going to learn stuff in this class. You're not going to be able to do the tests and quizzes. So I encourage you to do your homework, but as you can see, I don't give you 50% or 20% for doing homework. Most of your grade will have to do with your quizzes, the midterm, and the final. It's a department policy that you have to pass the final, which of course means you have to be here for the final. The final, I think, is on a Thursday on the Thursday of finals week. I will drop your lowest quiz if that helps your grade. If it doesn't help your grade, I won't drop it for you. That's just you know, you may just miss a class, or you may just have a bad day. And I tend to look, what's the word I'm looking for? if you go through the whole class and you kind of scrape through getting C's and D's, and then you come in and you get an A on the exam, and your average is really kind of a C, I'm likely to raise that to a B, because that suggests to me that you kind of figured out what you needed to do at the last minute, and you learned the material. I'm really mostly interested in you guys learning the material. So, I'm trying to think, is there anything else? Most of this other stuff is kind of pro forma stuff I copied from another teacher. But that's not saying it's not correct, it's just, I don't necessarily want to emphasize it. So, okay, are there any questions on the green sheet right now? Yes.
Question right here. The auto exam is the Tuesday, June 23rd, but the important dates right here is March 24th. I don't know.
Oh my gosh, you know what? I copied the wrong version. If you go to my website, you will get the correct information.
Sure.
I apologize about that. I got things. I think I actually have the correct version here, and I had an old version and I copied it. So keep that in mind. Yes.
Another formatting thing, we had homework sets and quizzes repeated twice. At once.
Yeah, that's okay. Thank you. I think it's right on the website. So now you can use this as, for making airplanes, I guess, or whatever. All right. Okay. I'm just going to repeat myself a little here. If you've never taken calculus, this is a hard class. It's not an impossible class, but you're going to have to study, you're going to have to come to class, you have to pay attention, do the homework. And if you find yourself in a position where you don't feel that's enough, we have a wonderful resource here called the PSME, no, it was called the PSME Center. It has a new name that I don't remember.
Student Learning Center, I think.
Say that loud, please.
STEM Student Learning Center, I think.
STEM Learning Center, yes. You can go down there, get free tutoring. They'll help you with your homework. They'll help you with any material you missed or you're having trouble with. I encourage you, if you're having trouble, to get help. What else do I want to say? What do I want to say? This is a long class. Runs from 1:30 to 3:45. And we will have a break in the middle. You will sometimes notice by the clock that I'm not looking at that I've gone over a little, and you're free to remind me that you need a break, okay? Don't feel bad about that. I will forget sometimes. Especially in a class like this, but in general, I'm fairly loose about turning in homework. I'd rather you do it and turn it in when you have a chance than you give up and say forget it. And I won't really dock you for it, turning it in late. Usually when we have homework, you bring in the homework, and we'll start the class with questions about it. So if you're having trouble with a problem, bring in, mark it, bring it in. Yes?
There won't be any online homework, right? Like website or my math class?
No, good question. I keep getting encouraged to use the web sign, and I keep beating my head against it. And I just, I'm going to try at least have the WebAssign problems up there, so if you want to go and practice, you will be able to. I don't think I'm going to assign it because it's just, what you have to do is hard, and what I have to do is hard too. I have to prepare for every class and correct your homework, and it's just, I just don't see benefit in it. If I saw a lot of benefit, I would. I'll try and set something up and give you the key so you can log in and then you can look at all the problems they have up there. almost everything. Let's just very, very briefly talk about what the background for this class is. You should have taken algebra, of course, and geometry in high school, pre-calculus, trig, functions, and first quarter of calculus. And things that you should know from that first quarter of calculus are, I guess I'm just going to put a list over here. So you need to know about limits, what a limit is, how to find one. Since we've covered 1A, a lot of times you'll find L'Hopital's rule to be useful. If I say anything up here for the prerequisites and you don't know what I'm talking about, please interrupt me and ask, okay? So I'm going to assume if I say something and I don't hear anything, everybody knows what it is. You need to know what continuity is. You need to know the definition. You need to know what a derivative is, what it means, how to calculate it. Specifically, you should know how to find the derivative of a polynomial, a rational function, exponential function. Let me just say exponential and log functions. And the trig functions and their inverses. You should know the general rules for finding derivatives, like derivative of the sum is the sum of the derivatives. You know the product rule. I guess I could write these down. Product, quotient, and the chain rule. And the derivative, you should know the definition of the derivative of an inverse function. And you should know, most importantly today, well, it'll be Thursday, you should know what an antiderivative is. Someone tell me what an antiderivative is?
Generally the opposite of the derivative.
Okay, so I have a very mild hearing problem. So if you talk clearly, I will have no trouble, but if you kind of talk, in this big room, there's a lot of echo that interferes. So you were saying?
The opposite of the derivative, generally the backwards function, the inverse.
Yeah, well, that's fine. Yeah, it's a function that if you took its derivative, you get what you started with. Okay, there's one more subject I want to talk about. It was a big deal. Any questions about any of this? No? Okay. It was a big deal in pre-calc. I'm hoping it will be a very small issue here. If I were to say, let's say, we'll make it real simple. If I were to say, what's the answer here? Yeah. So I would definitely be a little concerned if some of you go like let's see, 1 divided by 3. Now let's add 1 divided by 3. Oh, that's just, well, there are a lot of them.
So you prefer exact answers?
No, it's not a preference. I will either ask for an exact answer, in which case you need to know what that means. This is clearly not an exact answer. I don't care how many 6s you put on it, it's an approximation, right? I will ask for an exact answer, or I won't. If I don't ask for an exact answer, whale away on the calculator, figure out how many decimals seems appropriate, and I'm pretty easy on that. But if I said what's the arc cosine of 0, 0. You know what the arc cosine of 0 is? Well, you could try this, right? Right, that's, it's 1.57079632, no, it's not. That's great for engineering. And if, some of the problems in this class will be physics-oriented and engineering. If I don't ask for an exact answer, fine. This is pi over 2. All right, so just be aware if you see, typically on an exam, I've gotten used to writing really clearly exact, if that's what I want. The reason is very simple. Sometimes I want to know if you learned how to do something. And sure, you pop it into the calculator and you can get an approximate answer, but that doesn't tell me you knew how to do something. So, okay. All right, I'm going to take a second here. Are there any questions? We're going to start. Any other comments? All right. Okay. I'm not sure how this is going to work out. I'm going to try today just letting you guys sit wherever you want. If it doesn't work, I'm going to ask people to come a little closer, but that's fine. Okay, so we want to start. Erase this. We want to start talking about area. What do we know about area? I guess this goes back to our geometry class a long time ago. We know how to find the area of what? Triangles. This will do well for you. You still need to know that stuff, right? Rectangles, parallelograms. How do we find like the area of some bizarre polygon?
Split it above issues.
Yeah, we just split it up into triangles. Right? We can always do that. And we know the formula for a triangle. We have some values. We can do that. Certainly, circles. We all know the formula for a circle at this point. Pi r squared, thank you. There's some things that are a little more complicated that we've run into that we didn't really talk about the area. Probably haven't. If I were to show you an ellipse, no, that's a terrible ellipse, but we'll have to do it. It's like, well, so there's some form. There's probably some formula for this, but
Pi AB. there?
Probably has something to do with that. We can figure it out. We will figure it out. And then, you know, maybe we have like a parabola, and you pick some limit and you want to know the area under the parabola. Does anybody happen to know what the area is?
It's going to be an integral,
Hmm?
probably.
Speak up.
It's probably going to be an integral right there.
Integral?
Yeah.
Oh, we're going to need an integral. Yeah, that will do it. If you put a rectangle around a parabola, this is going to be 2/3 and this is going to be 1/3. We're going to figure out how to do all this. Okay. So the way we start this little adventure is we look at some generic function. I mean, you know, this will be, that looks, we'll give it a little, there we go, some kind of function. And we're going to ask, what is the area between, we're going to call this f of x. We're going to be doing that a lot. We're going to pick 2 points, A and B. We're going to say, what is the area between A and B and between this function and the x-axis? That sounds like a very restricted kind of problem. It turns out that once we learn how to do that, we're going to know how to do a lot of other things. Okay, so how might we go about doing this? Well, we could start by trying to approximate it. And the way we're going to approximate it is we're going to take this interval. Everybody familiar with this notation?
Yes.
Yeah. What kind of interval is this?
The
Closed.
Closed interval.
Thank you. Good. Okay. Everybody know this is how I write an open interval.
Which does not include A or B.
Right. Does include the endpoints. This is also how you write the point AB, and usually from context you can tell. But anyway, we're going to take AB and we're going to create from AB we're going to create a partition. And our partition is going to be a set of numbers. We're just going to call them x right now, x, 0, 1, 2, to x to the n, where these are all in order, strictly in order. None of them are equal. You know, there's something you're going to have to warn me about, which is if I get too low to the bottom here, and you can't see over the top, you'll have to let me know. I'm as far down as I can go. Where A is x naught, and B is x to the n. So, okay, let me kind of draw some of these in here. This is x naught, this is x1, this is x2, x3, and so forth, and then we have x to the n over here. Okay, and now we're going to take these kind of thin-shaped things that we're creating here with our partitions, and we're going to estimate, assuming these are kind of a rectangle, right? So we're going to have to pick some point between x0 and x1, and at that point, we're going to draw a rectangle. Okay. I'm going to leave this part out. This is just going to fill in here. Okay. And we're going to give a name. Yes, we'll start over here. We're going to give a name to those points we choose. So we're getting a little fancy here, but for the first one, we're going to call x1 star. That's this point over here. And we're going to have x2 star and all the way up to xn star. That's just the point on that small interval we chose. Again, we're just kind of picking something out of the blue. It could be x naught, or it could be x1, or any point in between. And we're going to sum, right? We're going to sum from n equals, say, I from 1 to n. What? Well, what's the area of a rectangle?
Base, its length times width.
It's length times width. So let's call this direction the length. What would the length be?
Star.
Yeah, f of xi star. And now the width, that has to be the difference between these two, right? So x of I plus 1 minus x of I. Right? So now we have some kind of estimate for our area. Now, you guys, you took calculus 1 and you had a derivative, and you start off with something like this. You say f prime x estimate, right? I'm going to get rid of that in a second. It's just take what? F of x plus some h minus f of x divided by h.
Yep.
And that's just an estimate of the slope, right? But when we want to get rid of this estimate, what do we do?
You take the limit as h goes to 0.
Right. Is everyone familiar with this formula? Anybody that's new? Okay. Anyone ever seen another version of it?
Yeah, the secant form.
I'm just thinking of the limit is x approaches a of, oh, I put it in the wrong place, sorry. H approaches 0. Sometimes you say is the limit as x approaches a of f of x plus a, yeah, f of x minus f of a all over x minus a. This is the other version. They both work. They're both the same. They just look, just in one case, h and a are substituted. Okay. So, okay, that's nice. What do you think I'm going to do over here? Well, it's not quite the same simple thing here. What we're going to do is we're going to take our partition, right? And let's give our partition an index, call it 0. And let's say that, I guess I want my partition here. Let's say I want a finer partition, more points in it. So I'm going to call P1 a partition which has all these points and more. I'm using less than kind of in a new, I don't mean like less than as in one number is smaller than the other. Clearly, the number of points is getting greater, but also this is a subset of this, right? If you like, P sum 0 is a subset of P sub 1. And then I can have a P2, and then I can just keep going. I can just keep adding points indefinitely. So now I can say the limit, I guess I should call this P sub P sub m. So I want to look at the limit of, let's say, P sub x as x goes to infinity. In other words, I take a limit where I just keep adding points, and these rectangles get smaller and smaller and smaller, and what happens to my area? Right?
It approaches the area.
Approaches what we're going to call the area. Now, is anyone here thinking of going on in math? I'll pretend someone raised their hand. One thing you might want to concern yourself with is, does that approach a limit? I mean, you know, this is math. You can't just assume things. Will it always, for any function? Is there some restrictions on the function? Okay, all right. You guys, you don't seem that jazzed about going on in math yet. But maybe you will. Maybe I'll get you excited. That's an important question.
Breaks down around asymptotes. Breaks down around asymptotes.
We could have some asymptotes. Yeah, that could be a problem.
Yeah, that's usually the most major problem.
Okay. Okay, so this is the traditional. Should I do this? Yeah. All right. I'll kind of throw the technology into high gear here for a really dumb reason. Hopefully this won't take too long. Which panel? Let's see, let's put the .cam over on the right. I'm not using those boards. Let's see. Let's see if that works. It'll come up in a minute. This sum here, we have. This is called a Riemann sum. I think that's two ends.
Yeah. 2 ends.
This group, they're way ahead of me. It's named after Bernhard Riemann, who, this isn't a history class, but sometimes it helps to kind of get a feel for when things happened in 1826, 1866. That's sad, he only lived to 40. There he is. There's Bernhard. Bernhard Riemann, mathematician who came up with this idea. This is kind of the start of integral calculus. However, it goes a little further. Sometimes what we're going to work with is known as a Riemann integral. And a Riemann integral works for just about everything you could ever want to use it for. If you're a scientist, an engineer, you're never going to care about anything else. There are some weird functions that this doesn't work for. We do have another integral that's useless for anything but weird stuff. So. Okay, that's all for the technology. We'll have somebody else to look at later. Okay. All right, so now we're going to do kind of a more practical kind of example here. And we're going to use a slightly less rigorous definition here. Let's see. Does everybody have this? Because you have it on your read sheet, so I'm not worried about it. We're going to look at a speed distance problem. Imagine for a minute you're in your speed car and you're traveling, I don't know, I think down I-5 towards LA, right? Maybe it's a Prius and you're saving a lot of gas, but you're still wondering, and you're not driving. Your partner's driving. And you don't have a map. And you're wondering, what do kids always ask their parents? Are they in the area? And you want to know how far we've gone. But from the back seat, you spy over and you can see the speedometer. So what you do is, say every 60 seconds, look over and you look at the speedometer, right? And it says something like, 60 miles per hour, or, on I-5, it's probably like 80 miles per hour, right? And you kind of write that down. Now, it might help to know that 60 miles per hour is, can we know how many feet per second that is? A good thing to know, a little factoid, 88 feet per second. So you go for 60 seconds, and you know how many feet per second you're going, and over that interval you know what? How far you've gone, right? So one way to think of it is this. There's some kind of function which is how far you've gone, right? Which is, increasing, right? You could look at the slope of this, and that would tell you what? Tell you this, right? Kind of graph, you can graph the slope. But what are we doing when we take this and we multiply it by 60 seconds? What are we doing?
Give the distance.
Taking a little rectangle here. No, that's not it. What we're doing is we're looking at the velocity now.
Velocity.
Right? And we're taking some x star point along it, and we're multiplying, we're figuring out this rectangle. And this is time, right? So what are we doing when we integrate, we're here, integrate across this function, this velocity function? What are we figuring out?
The approximate distance we travel.
Yeah, the distance, right? It's the complicated way of saying, velocity equals, distance equals velocity times time. This only works because we've got a constant velocity. Here we've got a changing velocity, so we have to kind of break this interval up, right? Okay, so let's give these things names. Let's kind of make a chart here. So we have time, right, and velocity. And our time is always, let's just say 1 minute. I like seconds. Let's go back to seconds. And let's just give our velocities an index. V1, V2, V3. And now, again, looking at this idea of a Riemann integral for a minute, we've got a sum, but our f of x is now what? It's just going to be v sub I, and I guess we're going we're going to change this. We're not going to call it 60. We're just going to call it delta t. It's some fixed. Okay. So if we take the sum of our velocities times our time, that's going to give us what? That's just our distance. Now, I don't know if you've worked much with sums, but if you have the sum of something times a constant, you know what you can do?
That's the other side.
Yeah, we can take this outside. So if we just add up our velocities and multiply by our time, we get our distance. All right. How could we improve on this? I mean, this is an approximation, right? How can we improve on this?
Increase the indexes to the large number.
Yes. And what would that do to delta t?
And make it smaller.
Yeah. So we're kind of looking for. I'm leaving out the extents here. You know, 'cause 0 is the first, 1 is the first, and n is the last. But this is just. We're setting delta t towards 0. So the smaller our interval, the more accurate we are, and the better our estimate is going to be. The other way you can look at this is I equals 1 to n. This is the same as saying setting n to infinity. Okay, this is kind of the same thing we were doing with area. Instead of an area, we're getting the distance.
Out of the velocity.
I'm sorry?
Out of the velocity.
Yeah, we're getting that from a velocity. Right. Okay. All right. I want to do a real practical application. You get that point yet? Need a break? All right, we'll do one more thing, and then we'll come back and we'll do some problems. I guess I don't need this. So let's do this. Okay, I'm going to take a real specific example here. I'm going to take a function f of x equals square root of x plus 2. And that kind of looks like there's 2. It goes off like this. And I'm going to ask the question, what's the area under here between 0 and 4? So, I think I'm going to create a little chart over here. We don't need this anymore. So my first estimate is going to be really rough. What I'm going to do is I'm just going to take my starting point. Let's see here. Again, I want to have a little chart. And I'm just going to break this up into one rectangle. So at 0, my function, f of 0, is what? It's 2. The distance is 4. So f of 0 times 4 is 8. And I'm going to call that my first lower estimate. But now I'd like another estimate. Instead of using the starting point, I'm going to use the end point. So f of 4 is what? 4. Okay. Keep awake with me for a few more minutes. So f of 4 times 4 is 16. Now that's this rectangle here, right? Now neither of these look very good. But at least I've put some bounds on here. Is it clear that the first estimate has to be less, right? I take a point which is, less than any other point on this. This area has to be less than the area under here. And this area, which is at the top, has to be greater. So, okay, so that's I'm kind of on the right track here. I'm going to redraw it. It'll be easier. 1, 2, 3, 4, 2. And now I'm going to break this up into 2 pieces. So here, for my lower estimate, I'm going to just take a rectangle here and a rectangle here. It's going to be my next lower estimate. All right, so let's see. So we've got f of 0, but now times 2, plus f of 2 times 2. Okay, now I kind of need a calculator, don't I? Right? So, well, f of 0 is 2. 2 times 2 plus square root of 2 times 2. So that's 2 square root of 2 times 2. And I'm just, all right, I get it. I didn't do that right. This is 4 plus 2 times the square root of 2. Okay. I'm doing something wrong here. Oh, no, I'm not. Why is that number less? That doesn't sound right. That's 8. Oh! Okay, f of 2 is not square root of 2. What's f of 2?
Square root of 2 plus 2. Square root of 2 plus 2.
Okay, times 2. All right, now we're doing a little better. 4 plus 2 square root of 2 plus 4. Okay, so it's really 8 plus 2 square root of 2. Okay, so that's 10.8. And what am I going to do next? Well, now I'm going to find the area under these 2 rectangles, right? So that's going to be f of 2 times 2 plus f of 4 times 2. This we already know is 2 square root of 2 plus 4. And what's f of 4? It's 4, so this is plus 8. A little tedious. This is 12 plus 2 square root of 2. Okay, so now this may seem a little obvious, but what's happening to these numbers?
They're getting closer to each other.
They're getting closer to each other. All right. So I now have 4 partitions. I'm not gonna do it. I'm just gonna read you the numbers. Okay. Right, so here we get 11.14. 4, and here we get 14.14. Okay, so you see what's going to happen as I go on here, right? These two are going to get closer and closer, and they're going to approach some number which we're going to call the area. Right? Okay. This is kind of, by hand. Now, we're going to make you do a little bit of that, just a little bit. Just, so hands bleed, and, it's part of the learning process. But we're not going to make you suffer through the whole course like this. Far be it. I guess I should turn it off. Okay, everybody see this okay? So here we have a TI computer, TI calculator, and in case you're not familiar, if you hit the Y equal button, you're going to see, you should see Y equal. If you don't see Y equal, go to your mode and take a look down here, and you see it says func, as in function, not parametric, polar, I don't know what sequence it is. And, oh, I did that wrong. I typed in 2 square root 2. I don't know why I did that. Use this X button here to enter the variable. So here we have square root of X plus 2. And it's always nice just to see that we're on the right track. Hit the graph button. And there's our graph. And you can see now second over trace is calc. Right? And if you look down here, number 7 is a little symbol. Some of you may be familiar with it already. It's the integral symbol. We're gonna see a lot of that in this class. And let's integrate f of x. So okay, let's hit that. And now it wants a lower limit. So our lower limit is going to be 0. And our upper limit is now 4. And here we see both the graphic impression of what the area looks like, and we have a value, which is 13.333371. So just so you understand, what the calculator is doing is just what we were doing, only it was using a very small number here. I think you might be able to look at the window, and I think one of these, I'm not sure actually, one of these might be the width, of the interval or the number. That's something for another day. When I was learning calculus, not only didn't we have graphing calculators that did our integrations for us, we didn't have calculators that added or multiplied for us either. That sounds like, like when the cavemen roamed the earth, but we had slide rules and tables, and I guess in college, the first kind of calculator, handheld scientific calculator came out. It was about $400. That's probably about $3,000 today, you can imagine. And it didn't do all this graphic stuff. It would just add and multiply and cosines and sines. It was pretty neat. Made by a company that you may have heard of called HP. Okay, I think we should take a break. You have time to run over to the the store and get something to drink if you want, or you can hang out here. I'm going to take a quick break, and then I'll have time to answer individual questions for a few minutes, and then we'll get started again. Okay? All right. Is it too hot in here? Because I can open the door and get a little breeze.
Yeah.
They gave you
Yeah, he really does get angry with that.
I mean, I didn't have to get a textbook last quarter because it was free.
Kind of great IS.
Yeah.
Well, my classes are.
Is that like super different from this one?
It is. I mean, he really. And that wasn't even speaking about the other 40 AP class. Pretty much about the call stuff.
I'm gonna try to see if we can get it. But it's like super.
Well, usually AM has a bad deal for a lot of people.
No, it's at like 6 to 8.
It's gonna slow.
Yeah.
Honestly, we're. Yeah. I want to do some things. Generally, hopefully it goes about it. Just something really about it. As a side effect of a series.
Did you read
songs? The series song of the summation of constant is multiplied by the times of sun. But it's good to know that stuff, but people substitutes finally forcing it down to the concept zeros and infinities is not a direction.
Yeah, it is kind of stuffy, isn't it?
Not much comprehension. I just go to this one last because I had last one.
So you're and why don't you put your name and your email, and then I have a
Last quarter, I used a different textbook.
I'm sorry?
And if you have like, okay, and if you have like the calendar of what we're gonna do, or like, will we just do like maybe
Yeah, it's approximately that. I will, this being the first time I've taught the course, I have a rough idea. But, and I tend to, when I develop lesson plans for myself, I put them on the website so you can look at them. So you can see as far ahead as I am. At some point I may be. Oh, sure. Yeah, the one, I mean, you will need the book for the homework problems.
I mean, I have this book, but I didn't use it last quarter.
So if you have it, sometimes there's not a problem. What we're doing starts. And
Looking at the, I don't think I've ever done this yet.
oh, well, that's, I don't know if that's part of the course either. That is applications of
We
differentiation.
did, the last quarter we did, like, I remember the last one we did was, she gave us like problems on like acceleration, and we needed to find, it was like applications, and we needed to find the position and the velocity, and, oh yeah, we did this too, the mean value theorem.
Yeah.
This book just looks really different from what I.
Is the other person who's adding,
Right.
could you put your name and email address, and I will try and get you an ad code by tomorrow. Actually, I'm doing the wrong thing here. Just to be efficient. Silver edition. It's perfectly okay to work with your fellow students on these if you want to. It's a practice. You feel confident, and you can just go ahead and do that. So here's the deal. I think there's a sign that says no food, but as long as you leave the place as clean as you left it, I can do it. There's no garbage can in here either, so when you're done, you have to. We just went on a trip down the Colorado River, and the rule going down the Colorado River is you can't leave anything. You can't leave anything. Okay.
Do they enforce it?
Yeah.
How do you enforce that?
With park rangers. To run a tour down it, you get licensed to do it. People who do it, they're very environmentalist. The reason they do it is because, pardon me, if all the people went down to Colorado, left their poop there, it would be quite a mess. So you gotta take it with you. So just remember, take the bag with you. Nothing here. While you're working, I just have a few random questions. I'm just curious. Who here is science-oriented? Physics, chem, medicine? Anybody business? Business people? Okay. Anything else? Oh, okay. Computer science. I should throw this out that for the last 35 years I've made my living in computer programming, for the most part, except for the teaching.
You try doing FLs?
Sorry?
Functional languages? Scala, Clojure, Haskell, Camel?
I can name random programming languages too.
They're FLs.
Snowball, COBOL, Algol, Fortran.
Fortran's kind of the same. Nowadays, everybody likes scripted languages as a preference. But there was a guy that felt like doing his research paper in Fortran.
It's amazing. It's still around, but it's because the scientific community has so much vested in it.
And it's extremely fast for what it does.
I don't think any faster than C.
C has large problems with many cases, and you can fake types with both, but one can do a bit more mathematically.
Yes.
What's it like working as a coder?
Well, so for about 6 years, I worked for businesses in the 70s, early 80s, and all mainframe, no PCs. And, can see in the last decade, a lot of them. So, you know, it's hard now to be an independent consultant, right? I've done a niche, but if you can work on your own hours, contract work, it's really nice. You have to like it, I think. Some people ask, you have to like it. I mean, if you can do it, but you don't like it, you can do a lot of other things that you like more. Some people just, you know, it's funny, it's just kind of your nose is, you know, like right in there, every comma, right? You drive you crazy, but after a while it doesn't. There's a lot of art to it too. Learn how to think. We first learn how to think, how do I make a little piece of code do something? And then you start thinking, how do I build a system that is going to, not that it won't have bugs, because they always have bugs. When it has bugs, I can find them. So, I mean, it seems to be right. The only thing I'll say about the field is that it's kind of a little roller coasterish. You know, it has ups and downs. In the around 2000, there was a tech crash. A lot of people were out of work. It was a.com bubble, yeah. And then a few years ago, when we had the big, you know, 2008. Tech didn't do as bad, but they stopped hiring contractors. So, you know, it's got its ups and downs. But, you know, I think that's, you know, things have changed. Like, when I grew up in the 60s, people thought in terms of going to work for some corporation for their career. They were really interested in, like, do they have a pension plan and stuff. Apparently, there aren't very many companies like that anymore. They don't have much loyalty to their employees, and so it doesn't really benefit their employees, except while working there, to have loyalty to the company. You know, people, if they see something better somewhere else, they say, okay. It seems to be the case.
And IT is generally undervalued. It's extremely so
That's, I agree. That's a big problem. And one way, when the PC came out, one way to leverage that was to say, all right, I won't work for you, I'll just make my own products. Start my own company.
This is visibility there.
It depends. If you find a niche where you're visible, then, which I did actually for a long time. But yeah, life is complicated now, isn't it? But, you know, we have all these, the whole internet. You can start a, you know, I mean, you could advertise your product on Twitter or something.
And you can find bizarre...
Create your own website. Pardon?
And you can find open source selling software, weird things like that.
Yeah.
And then there's
So I will say this, you know, if you're in that place, you know, I'm like, what the heck do I do with my life? For something you enjoy, I mean, you know, and be persistent about it, you know, and don't fool yourself, you know. I think the thing I see most common is people fool themselves into thinking, I like that job because it makes a lot of money. Now, that's not to say that making money isn't important.
for fun.
For some people, making a lot of money, maybe they feel it's important. But you know, at the end of the day, you come home and, you know, either like what you're doing or you don't, right? And some people paint themselves into a corner. I'll tell you the profession that I run into the most where people who have gone to school and gotten a degree or whatever, credential, and don't do it, is the law. I don't know why that is. I'm not saying there aren't, I have friends who are good lawyers and they like it. That, you know, I've seen people, high school teachers, programmers, you know, whatever, you know, business, but maybe there are too many lawyers, I don't know. How are we doing? Is everybody's knuckles bloody with 1 and 2? Anybody have a question about 1? Is anybody not done with 1? Sir? Anybody not done with 2? Is anybody just not answering because they're shy? All right. I don't know. You know. Let's see. Let's see if what I do has anything to. So for the lower, I'd say F0 plus 0.25 plus F0.50 plus F0.75 times 0.25, that would be my lower. My upper would be 0.25. Oh, I don't actually know if those, yeah, they're going to be lowers. 0.5 plus 2.75 plus 0.25. So I guess I could leverage that a little, couldn't I? Oh, I left one out. Plus F1. So if I just kind of calculate this, just do it once, right? So that's going to be 6 plus 25 cubed plus 5 cubed plus 6.5625. If I add 2, what am I, 2.25, I get 2.1625. Instead, 3. Yeah. 2.390625. Is that what those are to do? Oh, I have to draw it too. So. Oh, I guess I need to make the axes look a little better. So, that's 1. Am I allowed to have different scales on my axes? Oh, good, okay. 1, 2, 3. So, start 2, we go to 3. Okay. So I have, I'll just draw my lower. It's my 2.140625. And I'm not going to draw the other one because I'm lazy. All right, we both ended up with that. Yeah. There must be some logical reason for that. I'm just curious with the average of these two. It's 2.265625. And then so what's there? 2 plus x cubed. And let's find distance between 0 and 1. Okay, this thing says 2.25. Anybody want to make an observation about just by breaking it up into 4 pieces and then taking the average of the upper and the lower? That's it's almost 0.5%, only 0.5% off. Pretty close. See, we don't care if it's wrong. Right? I mean, if you're an engineer, it's fine, right? But it's not mathematically precise yet. Okay. I'm not saying this to point out somebody's slow or embarrass anybody, but I'm trying to find out where you're up to. Is anybody not working on 5 yet? Okay, right. We need some more time. How about 4? Anyone not working on 4 yet? Okay. Are you working on 3? You did a really careful job on those graphs, right? Okay, all right. Did anybody get anything different than I did? Because
What did you get for number 2?
nothing yet.
Oh, I thought you were already doing number 2, sorry.
Okay. I'll work on number 2, right? So f of x is equal to 1x plus 1 squared x. Again, I'm just asking this because I don't really know what other teachers do. Does everyone know what this little symbol is?
It's part of it's an element of that set.
Yeah. Does everybody know that? That's what this. It's not the epsilon. God, you really, in my handwriting, you're never going to tell the difference. This is kind of like this. This is inclusion. And I think you've probably seen epsilon, which is Greek letter meaning that small, tiny thing, right? Okay, so zero is 1. 1 is 4th. 1/8. Okay, so we've got one of these guys. So we're going to sum these. So f of 0 plus f of 5 plus f of 1 plus f of 25. That's actually going to be my upper, because this is a decreasing function. All times 0.5. Or f of 0.5 plus f of 1 plus f of 1.5 plus f of 2 times 0.5. So again, I'm gonna leverage this. So I'll do some of this by hand. So this is 1, 1/4, 1/2, 3/2, 9/4. This is 4/9. And 1.5, that's 3/2 plus 1 is 5/2, 25/4. 4/25. Oh, you know what? You can do that one exactly. I'll bet nobody's going to do that, right? I'll do it. So I just need to find the common. Anyone know what the common denominator for these is? No whiz kids yet. 100 plus, let's see, 9 times 25, it's 9 times 25, 225, 4 plus 900 plus 4, 16 times 44, at times 1/2. So that's 13. Get all excited about this adding. I should be an accountant, right? 13, 15, 25 plus 1669. 69 over 1800. Well, now I'm going to get a number 9 divided by 0.9272 repeating. All right. So we have 4/9 plus 1/4 plus 4 25ths plus 2 3 plus 1/9. Right. So just just make that 5/9. Again, it's 900. So 5. Oh, wait. What am I missing? Oh, I'm not missing. Okay. Plus We did this. Is 9. That's got to be 225 plus 4, 6. Oh, it's 244. So 725 and 44, 9, 6, 869. I feel like I've made a mistake here somewhere. I feel like I must have. Just a little foolish. So that's not really 7 repeating. So let's add those two together. 0.9, 2, 7, 2. Let's divide by 2. I get 0.705. Okay. Who is it who's asking me about number 2? Okay, so again, the function is 1 divided by x plus 1 quantity squared. And let's make sure that graph, yeah, that looks okay. Right? And now let's calculate from 0 to 2. Yeah, I must have made this. Maybe not. My estimate of 0.70 is not that good, but it's not that far off either. Oh, is anybody working on 6? Oh, we didn't really talk about that, did we? Have you come up with a strategy? Or are you just sticking it in the calculator?
Subtract 1 from the other.
Oh, don't give it away. Yeah, that's yeah, I think you can subtract 1 from the other. Let's take a little look at that. Can I erase this? This is, I think, was part of number 1. Okay, let me check it. Find the area bounded above by net. Oh wait, there's more than just subtracting here, isn't there? But let's take a look at it, right? That would be a good thing to do. I mean, you know, I could say, tell me what it looks like. But I'm not going to do that. I'm going to just say, let's see what it looks like. Let me give us some idea what to do here. That didn't work. Joys of computers. It doesn't like it. Oh, I don't like it. What's wrong with that?
The minus, it has to be the negative
Oh,
sign.
thank you. Yeah. Usually I remember that. Aha, so these both look symmetric. Yeah, they are both symmetric. So what do we need to do? We need to find out where they intersect, right?
Algebra.
Told you. Need algebra. So y equals negative x squared. This is easy. What do you think I should do? I mean, this isn't something you did in high school, but you guys are college students. You should be brave, right? You're in calculus. Let's just substitute that in. All right. So 2y equals 8, or y equals 4.
Plus or minus.
No. Look at this.
Oh,
Y equals 4. I didn't say what x was. 4 equals x squared. Now it's x equals plus or minus 2. Right. So now, you're foreshadowing a little here. We're going to integrate from negative 2 to 2 of, well, this is the upper one, right? Negative x squared plus 8 minus the lower one. So this is negative 2x squared plus 8. So I guess we want to put in that function, don't we? Do that. Insert 2. That. Now, minus 2, 21 1/3, it looks like.
Don't we just want the first quadrant though? Or this portion of the first quadrant?
Well, you see, you would get full credit on your test for reading the directions, and I would get a severe. I mean, if I was reading your test and he just didn't read the directions, but he knows his calculus, I'm like, oh, I'm gonna take a point off here, right? Yeah. So, how much? How do you think that affects my answer?
Should divide by 2.
Everybody, do you see why that is? It's symmetric on the this y-axis. So yeah, it's going to be half of that. Hey, somebody's good with calculators. This calculator. Is there some way to pop that number into my thing here? Is that like? Oh, asked and answered. I didn't know that worked. Okay.
Store today.
Smart.
Store that in today and then subtract it.
That's if I want to keep it. I'm just, if you think if, when I'm over here in calc that I can do that? I said, okay, so if I say store, I think I can say store here.
We'll work with answers, so you're going to have to
Store. Oh, well, yeah. It's going to work because answer has the value.
store it to a variable.
Do that? No.
Just
Well, anyway, really all I wanted to do was divide it by 2. There we go. 10 2/3. All right. Are there? I know not everybody's done. Is there any other questions about this? Anybody having any, just want to know answers? Now, I guess I should admit something, which is, I hope this is useful, getting your knuckles bloody here with this. I had a philosophical discussion with another teacher here, and she convinced me I should make you do this. But there's an easy way to do it, and I don't mean with a calculator. Or at least I think it's the easy way at exact answers. But I think there's something, she convinced me there was something to be said for struggling with this a little and kind of getting a feel for it, so I went along. Piece of paper I'm looking for. There it is. You don't have to write this down if you have a computer at home with the internet. There's an assignment. Again, a few more of these. You're going to get your knuckles bloody. But I think we're gonna move on a little bit. You are free to finish this up if you want. You can hand it in as part of the homework if you like. Okay, just state the law on there. I'd like to look at it. Yes.
Are those problems on your website?
These?
Yeah.
Yes, under handouts.
Oh,
You'll find when I make something up or steal it from somewhere else and hand it out in class, there's a section, handouts. Yeah, let's, we're going to do something else here. We've got some time, and this is a good place to start. So let's start real easy. This will be like a game show. You can rack up points. So if f prime of x is equal to x, what is f of x? What is f of x equal to?
1/2 x squared.
I'm going to write it like this. Okay. Let's just jump right in there and say x of n, where yes, n is not equal to -1.
X to the n plus 1 over n.
Now,
Plus 1.
did everyone just hear that? And first, I plug in, it's a class. It's got to be brave. So I'm not trying to embarrass you. I'm trying to teach a point here. Did you notice there was a little bit of lack of confidence in that, right? It's like, I'm not 100% sure, right? So the great thing about finding antiderivatives is that we're good at finding derivatives, right? Right? This is 1 over n x to the n plus 1. That's just a constant. So what is the derivative? We can check ourselves here. What is the derivative of 1 over n x to the n plus 1? Well, that's 1 over n. And then we multiply x to the n plus 1 times n plus 1. And then we subtract 1 from that, x to the n. Okay, so we're obviously a little off. So we just immediately go, aha, if we make that plus 1, now we got it, right? Never be afraid to check yourself, right? Especially on an exam. You know, okay. Thank you for, nobody else was brave enough to stay, so you get a lot from it. Okay. Oh, now, does anybody know why I did that? Let's see. That was n not equal to minus 1. Let's see how good this group is.
Ln x?
I heard something of x.
Ln?
I never know how to pronounce that either.
Natural
There's no
log.
vowel.
Natural log.
Yeah. And on top of this, you know, there's like, how does this work? So if you're in high school, or if you're an engineer, this means
Base 10
log 10 of x,
is common law.
right? But if you're a mathematician, this is log base e of x, better known as log of x. This is unambiguous, right? This can be, depending upon what kind of class you're in. And then log 10, everybody knows what that is. All right, yeah, it's the natural log. Oh boy, you guys know about E. Okay, good. I can't amaze you with that. All right, moving along here with our game show. Prime of x equals 3x squared plus 5x plus 9. Okay, so f of x. There's nothing new here except the plus. So what's that?
X cubed plus 5 x squared
Plus 5 squared over 2 plus 9x, if you like, over 1. Now, these statements are all true in the sense that if you find the derivative of this, you have found this. That is, you found an antiderivative.
It's missing the constant.
Maybe the constant is 0, right?
Yeah.
And then it's not missing it. Yeah. We don't really know.
Still missing
We
it.
know that we don't really know what to do with this yet. Maybe we will. We'll figure it out. You can add a constant to any of these, and it works because the derivative of the constant is 0, and that works. Everybody should know that. Okay, we're not done. We haven't had enough fun yet. We're going to switch over. F prime. So f of x is equal to
E to the x.
If I don't write the C, you can, you know, when you go to rate your professor, you can now, well, we're not going to get complicated yet. I'm trying to keep it on the level here. So that's prime of x equals sine of x. So f of x equals
Alpha C cosine x plus C.
cosine of x. Okay, so everybody remember derivative of the sine is the cosine, or cosine negative sine. So when you're going backwards, any derivative of the sine has a negative. Any derivative of the cosine is just the sine. Now, there are things that are more complicated, like, say,
Secant tangent. Maybe.
yeah, maybe. That's why you're in this class. We're going to learn how to figure these things out. So if you don't know what this is, don't worry about it. What you should know is things where we did a derivative, and it's pretty straightforward. You need that skill to be able to kind of go backwards. But you don't have to magically know the antiderivative. We're gonna spend over the next few weeks. We're gonna learn how to antiderivative a lot of weird stuff, and we'll be good at it because we're gonna, because we're smart, I guess. But don't worry about that now. Just the basics, right? Just the basics. You need the basics. And I think we have, let's see, what can I do? What part of the magic show can I do without giving away the secret? Okay. Okay. Let's do something which is it's notation, and some of you, I guess, are probably familiar with it. Oh, it's right there. We'll just go over this, and then I think we'll finish up. So I'm going to talk about something called the definite integral.
We don't even know the squiggle line for the indefinite line.
Sorry, I heard squiggle line.
For the indefinite line.
We haven't gotten to anything called an indefinite integral yet. I mean, we could, and then I could give you the final exam on Thursday instead. Say it's fine. Okay, so before we were looking at some sums where f star I sum from I equals 1 to n. Where we picked, I guess that's not really how we did this, that's how I did it the first time. Starting with 0 times delta x, where delta x was b minus a over n. Okay, by that I mean I'm looking at some function, I'm trying to add up the area between a and b, and I guess I have to embellish a little here. I have to call this xi sub L. This isn't xi sub star, just any old point. It's the lowest point in that interval. And then over here we have the same thing, except we have x I sub h times delta x. So these are those two sums where one of them was always bigger, one was always smaller, and between these, didn't leave enough room, so I'm just going to draw it down here. There's this thing we call the definite integral from a to b, f of x, and then this is, we're going to talk about this, but this is notation, say dx. Does anyone here recall hearing about Leibniz when you're doing integration? Not integration, derivatives? You know, there's Newton, where we say we have some function f of x, and we find the derivative f prime of x. Or the second, I guess you did second derivatives, right? F double prime of x. And that's Newton, or Newtonian. And then we have a different set of terminology. We have f of x, and we would say, we might say d dx f of x, or we might say dy dx. And this is the Leibniz notation. This is no small deal, actually. Newton was from England, and France was from, I'm sorry, Leibniz was from France. Yes, I got that backwards. And there was kind of a big, it was a big deal, you know, they both kind of came up with calculus at the same time, and who's better? And I don't know if you know any history, but there's been a little bit of conflict between England and France over the centuries.
America.
Well, it came over, I mean, when we fought against the British, the French, you know, Lavoisier, you know, Lavoisier? No. What was the French guy who helped us out? Thomas Jefferson went over, and I'm not a history professor. All right. So here we have Mr. Gottfried Wilhelm von Leibniz. God, with a name like that, you think he's German. I'm pretty sure he was French, though. And he came up with this notation. When I say notation, I just mean it's the way we write it. So this is our integral, our definite integral. It has, see, I'm not a historian. This is our lower limit, and this is our upper limit. And this is our integrand. And the nice thing about this is you can kind of visualize this as, you know, we're breaking this up into pieces, these delta x's. And as we break it up more and more and more and more and more, they get smaller and smaller and smaller. And instead of a delta x, they kind of go to a dx. Now, that's a way to visualize it, to think about it. Do not be fooled. We are not taking an infinite number of points, plugging them into f of x, and multiplying them by 0. Right? Because that's dx is basically, it's called an infinitesimal. It's basically 0. So don't take it as far as it's useful, but do not overdo it. I mean, I'll give you my other favorite example, which is the chain rule, which says, in Leibniz notation, dy dx equals dy du dx. Everybody familiar with that?
Yes.
Yeah. Now, I know it's like, it's perfectly okay. This is real multiplication here, right? There's nothing funny going on there. It's perfectly okay you want to remember it, to think, well, it's like a fraction. But it ain't a fraction, right? These are functions, and you can do that. It works out, but be careful. Don't fool yourself into thinking that's actually what's happening.
They're not numbers.
They're not numbers, correct? They're not denominators and numerators. Okay, and the same thing here. This is not like a really, really, really tiny delta x. But if you want to think of it that way, if it helps you to kind of get a feel for what's going on, that's perfectly okay. All right, so this is what we call the definite integral. There's something you should know about it. It has an x in it. In fact, it has two x's. It's not a function, it's a number. There's some value associated with it. So whenever you see something like this, like if I said, what is the derivative? Here, I can do something tricky that you'll never see in real life. It's best, these are what we call dummy variables. You can change them. It's best not to use the same variable. If I said, what is the derivative of this? Right? So I'll put that on the first exam, and most of you, you're not that confident in calculus. You're not that afraid. You kind of go, well, I have no idea. But it's really just, A to B, f of u, du. That's what it is. The derivative of this is this, because this is just a number. This is like a. So the derivative is just that constant. Right? So don't let, well, we'll talk about this a lot more, but that's just an important thing to keep in mind. It's a number. What else do I want to say about this? I think that's it. That's it for today.